And tonight in our lecture with Brian Schmidt, we've got a person who led the charge to discover two of the extraordinarily open questions in cosmology, dark energy and dark matter. They're there, they do things, but what are they? And Brian has not only led the charge to identify, I think it was the dark energy, but has now got the opportunity through his ongoing work to be part of the cohort of scientists worldwide who will be trying to understand what it actually is. So I'm very much looking forward to it, and thank you very much for the opportunity to speak to you. I now would like to invite John Latanzio, who heads our Astrophysics department, to do an introduction to Brian.
Thanks very much. Well, it's of course a pleasure to introduce Brian. We've been friends for a long time, probably since he arrived in Australia. We met very soon after, and he's been a continual supporter of the research that we do here, and has worked closely with us in many of our endeavours. And in fact, at one stage, when we introduced the honours program in astrophysics, Brian was taking our honours students away observing with him on the 2.3 metre at Siding Springs Observatory. And the students would stay in a cottage, and I believe there were even times when you used to go around and cook them dinner. So I don't think there are many students who can claim that on a field trip they had a Nobel Prize winner cook them dinner. But I know Brian has done that. So he's one of the good guys, and he's also a good scientist, which is why he's here tonight. And I believe this is the first public lecture in Australia since you won the prize. So please, can we all make Brian very welcome? Thanks, Brian.
Thank you. Thank you very much. Thank you, John. Thank you, Alan. And thank you, everyone, for showing up. It looks like almost exactly the right number of people showed up. That is, a couple of you don't have seats, but it's nice to see that the place is full. Anyway, it's my pleasure to be able to, I guess, sort of tell you the scientific story behind the Nobel Prize, what I call the path to measuring the accelerating universe. Now, don't worry if you don't understand exactly what I'm talking about. I'm going to explain what everyone's been talking about along the way, and I'll just mention that Alan, who's your chancellor here at Monash, is also the head of our Castro ARC Center of Excellence Advisory Board, and so it's great to have him on board, and I know he's a great asset here at Monash. So let's get right to it, and let's talk about how we started to understand the universe. It was really, I think, began observationally with this person named Vesto Melvin Slipher, who most of you do not know, but he is one of the greats of our field because he did something unique in 1916. He took the light from galaxies. Galaxies are collections of millions of stars, but they didn't even know what they were back then in 1916. And he spread them out into the colors of the rainbow. And he went and he noticed that when you spread out, and this has been known for the last 30 to 50 years, that if you spread the light of, for example, the sun out, you would see what we call lines or lack of color. And those lack of color identify different elements. So, for example, sodium absorbs or emits light in the orange. There's two little absorptions right here, which are when you go out near the airport or something, you'll see these very yellowy, orangey lights. Those are sodium lamps, and they're producing that color. So we can actually, if we spread the light out into these spectra, we can identify things in stars using these color absorptions. But when he went and he looked at the light from galaxies, he saw these absorptions, but they were not where they were on Earth. They were stretched redward. Now, we knew that that light was a wave, and that the wavelength of light tells you its color. So if you think waves have peaks and troughs. If those peaks and troughs are together, the light is blue. They're further apart, they're red. And so what he realized was that it seemed to be that these galaxies were moving away from us. As an object is moving away from you, just like the pitch of, for example, an ambulance, when it moves away from you, is lower than when it's moving towards you. That's the Doppler shift applied to sound. With light, you can use the color to tell you whether or not an object is moving away from you or towards you. And what he found in 1916 was that essentially everything he measured, every galaxy he measured, was moving away from us. Now, this was a cosmic conundrum in 1916 because it seemed that we were in a special place in the universe. Since the time of Copernicus, we thought we weren't in a special place, that everyone should see the same thing. And suddenly we saw the idea that we were in a special place, an unpopular place in the universe where things were gradually or quite quickly moving away. So that was a mystery in 1916. It was resolved by going out and measuring distances. Now, astronomers struggle to measure distances because we can't just lay down a ruler between us and the nearest galaxy. It's too far. But what we can do is we can measure how bright an object is. Now, an object's brightness depends on how far away it is. So you can see here, if you have a candle and you put it further and further away, it's going to become fainter and fainter as it's further and further away. Hubble used this idea in 1929 using the largest telescope of the day, the Hooker 100-inch telescope. And what he did is he looked out how bright the brightest stars were in these nearby galaxies that Slipher had observed. And what he found was that the further the galaxy was away, that is, the fainter the stars were, the faster the object was moving away. And with that observation, he proclaimed in 1929 that that meant that the universe was expanding. Now, why would he have said that? Well, here's his data, and I want to show you Hubble's data, because he's a famous guy. And you can see here his galaxies, the further the objects were away, or the fainter the stars. And this axis is the faster they're moving away from us. This is 0 kilometers per second. This is 1,000 kilometers per second. So 1,000 kilometers per second is moving right along. You know, that'll get you to Sydney in less than a second. It would be a very useful high-speed train. So, but that's what his data looks like, and it's nothing special, but you get the basic trend. That was enough to make Hubble famous. So, imagine you have a universe where I'm going to expand the universe, okay? And through the magic of my computer, I will hopefully let this universe expand, and I want you to see what happens. So, for example, imagine I'm here and I expand the universe, then nearby objects move a little bit, distant objects move a lot. The further away you are, the faster you move. And the beautiful thing is it doesn't matter where you are in the universe, everywhere in the universe sees the same thing. They see what Hubble saw. The further away an object is, the faster it's moving. That happens if the universe is expanding. Now, it turns out we had another reason to suspect the universe might be expanding, and that is thanks to sort of the heavyweight of physics of the 20th century, Albert Einstein, who in 1907 had what he described as his most wonderful thought. And that thought was that acceleration and gravity are the same. What's that mean? It means that if I stick you in an elevator in space and I make it accelerate upwards, there is no way to tell the difference between that and if I'm just on Earth with normal gravity. That is what we call the equivalence principle. And it sounds kind of trivial, but from that, 8 years later, in 1915, with him working on nothing but this, Albert Einstein, he came up with his theory of gravity, what we call general relativity. And so it was a hard deal, and anyone who's taken general relativity can attest to the fact that the mathematics is hard. It took Einstein 8 years. So that is how we understand the expanding universe, is through Einstein's equations. One of the reasons, just to give you a piece of history, is that Einstein's equations were important because they allowed us to solve cosmology for the first time, to understand how the universe will change over time. That was something that Newton could never figure out with his version of gravity. And the experiment that really showed that general relativity was correct was actually done here in Australia. Now, there was an experiment done not in Australia by a theorist, and theorists should never ever be allowed to touch data because they always sort of know the answer. And so I will just say that I think it is widely accepted by people who do the work that the actual test of general relativity, where we saw light being bent by the sun, was done in 1922 in Australia by 2 American astronomers. Anyway, one of the things that Einstein did when he tried his new gravity on cosmology is it meant that he found that the universe should be in motion. And this was in 1917. But the universe was thought to be static, wasn't in motion at all in 1917. So he had to fudge the result. And that fudge was known as the cosmological constant. It turns out that if you add energy to space itself, which is what Einstein did, so that's saying every piece of space has energy that's part of space itself. It's sort of like the ether, if you want to think of it. It turns out that this stuff will cause gravity to push rather than pull. We always think that gravity just attracts. But it turns out, according to Einstein's equations, it doesn't have to. If you make some weird stuff, it will do weird things. And so, in the end, once it was realized in 1929 that the universe was expanding, he retracted it and said, oh, that was a silly thing to do, and we moved on. The other thing to realize is that in Einstein's version of the universe, when you look at something, when you look a long ways away, the light takes billions of years to reach you sometimes. And so we have at our we have a tool of looking back in time by looking at very distant objects. So we have a time machine. Now, we can't look forward. We can only look backwards in time. The other thing is that rather than the Doppler shift, the idea that it's caused by an object's velocity, you can imagine that Einstein's equations tell you that space itself is expanding. It's stretching. And so that a light wave, which remember is a wave, as it travels through the universe, as the universe is expanding, it gets stretched with the universe. And that is what causes the redshift. And this is all understood through general relativity. And so the more the light travels through the universe, the more it expands, the more it's stretched. All right, so imagine we have this universe that's expanding. Well, it's going to get bigger, but we can run it in reverse. And if you go back far enough in time, everything will be on top of everything else. That naturally brings you to the idea of the Big Bang, the time when everything in the universe was on top of everything else. So imagine I go through and I think about a galaxy that is away from, for example, our own galaxy, the Milky Way right now, at this time, and I trace back what happens to the universe back in time. Well, I can draw a line, and this line is what we now call Hubble's constant. That is how fast the universe is expanding. We named it after Hubble. And it tells you, essentially, if you know how fast the universe is expanding now, you can extrapolate back in time and find out when the Big Bang happened by how fast the universe is expanding. Now, this is what I did for my PhD thesis. Just before coming to Australia, I, for my PhD thesis, measured how fast the universe was expanding. Now, I got an answer which was more or less correct, actually very close to the correct answer, but I won't say that I completely convinced the world. That actually was done by another Australian astronomer, my boss at the time, Professor Jeremy Mould, and a team from the United States, who used the Hubble Space Telescope. The good news is we got almost the same answer to a few percent. So I got a check for my thesis by my boss. So the answer we got was, in astronomers' unit, that the Hubble constant is about 70. I'm not going to tell you what that means, but I will say it means 14 billion years old is how old the universe is from the current rate of expansion. So how fast the universe is expanding tells us how old the universe is, but there's something I haven't told you about. We have gravity in the universe, and gravity pulls on all of the universe, and according to Einstein's equations and your own intuition, it will slow the expansion of the universe down over time. So we have to worry about that. Imagine the universe has a lot of stuff in it. Then instead of this trajectory, it will be expanding faster in the past, and it will slow down over time. So it will do a different trajectory, and the universe will not be as old as we think. Now, in 1994, when I came to Australia, the uncertainty in how much gravity there was in the universe meant that the universe could be 13 billion years old, or 14 billion years old, or it could be 9 billion years old. Now, the 9 billion years old was a bit of a problem because it was the most popular model for things in the universe. But we knew there were stars in the universe that were 12 billion years old. And it's not a good theory that has things older in it than the universe is old. So that was a bit of a problem. One of the interesting things about this type of universe is if you project forward, imagine a universe that has nothing in it, so it's not slowing down. Well, that universe gets bigger and bigger and bigger over time. It's infinite into the future. It never ends. It goes on forever. Imagine a universe that has a lot of stuff in it. It's a universe that it will expand, eventually halt, and gravity will then pull it back in just like a ball that I throw up in the air. And that universe will end not in a Big Bang, but in the Big Bang backwards, also known as a Gnad-Gibb. All right. So in 1994, when I came to Australia, I wanted to do something big. I always like to say, work on something you can explain to your grandmother. So I explained this to my grandmother. She said, okay, sounds like a good idea, son. And imagine a universe where I go back in time. I go back and I measure, like my thesis, how fast the universe is expanding now. And then I look back 10 billion years into the past, and I see that the universe has neither sped up or slowed down. That means the universe hasn't changed in its expansion over time. That's an empty universe. There's nothing in it, or very little in it. On the other hand, imagine a universe that will eventually stop its expansion and then collapse. Well, that's a universe that has a lot of stuff in it. You will be expanding faster in the past and has slowed down. It will have a different trajectory than one that is empty. So if we look back in time and we measure how fast the universe is expanding back in time, we can sort of judge what the universe has done over the past 10 billion years or so, and then hopefully gauge what it will do in the future. So on this side of this line, when we do this experiment, gravity wins. On this side of this line, gravity loses. Of course, if the universe is doing something funny, like speeding up, and just to have the idea of what it's like when a universe is speeding up, that's like me taking a ball out here, throwing it up in the air, and it to go faster and faster and take off and go off into interplanetary space. Now that would be a pretty amazing ball. I think it was, there was a show when I was a kid, a Disney show, where this stuff was flubber. Was invented, and so that would be good stuff to know about. And that's what would happen if we are going to have the experiment be up in this part of the diagram. All right. So to be clear, what we're going to do is we're going to measure how much stuff is stretched, low amount of stretching, a lot of stretching, and we're going to look at an object, and we're going to say, is it brighter and closer, or is it fainter and further? That's how this experiment's going to work. So, oh boy, this is interesting. This is... I'm going to move forward just a little bit because I am showing you the wrong talk. One moment. Unless you want a lot of equations. I don't think you want a lot of equations. So what I was going to show you next was, stuff like, well, you really don't want to see this stuff. But I'm going to move slightly. I'm not sure... here we go. This is just a little embarrassing. I apologize. You can tell I haven't given this talk yet here in Australia. All right. So yes, I was going to go into a bunch of differential equations for you and show you the real equations. This was for my third and fourth year physics students. So I give them an easy beginning and then make it hard. So the slowing down of the universe, it turns out, affects how old we think the universe is from the Hubble constant. Okay? It also tells us the ultimate fate of the universe, but it turns out it also tells us the shape and weight of the universe. How does that work? Well, Einstein's theory of general relativity, to make everything work, he had to allow gravity to bend space itself so that light actually won't travel in straight lines anymore. It travels the way that it needs to get through space as fast as possible. And so the idea behind Einstein's equations is that if you have a really heavy universe that reaches a maximum size and collapses, that is a universe which actually bends onto itself. This is a universe that if I head out this direction, with a sufficient amount of time, I will end up where I started. It's what we call a closed universe. It's finite. So it's a universe that's finite in time, but it's also finite in space. On the other hand, if we have a light universe, it turns out it bends away from itself, sort of like a saddle. And finally, we have the just right universe. It's the universe that is precariously balanced upon being infinite and finite. We call it flat, but it's also just right because theorists who want to understand how the universe got going right after the Big Bang always told me that this is the only way that made sense for them, that the universe should be constructed. So I never believe theorists, as you've already got an idea, so I always want to go out and test what they say. So we went through, and we've already seen this slide, and I apologize, we'll move past. We wanted to make this experiment with the brightest thing we could see across the universe that we thought we knew how bright it was. Remember, the fainter an object is, the further away it is. Well, that's true if you think they're all the same brightness. And so we have this great thing in the universe called type 1a supernovae. What is a type 1a supernova? Well, let's just do a quick run through our solar system. We're 5 billion years before our sun becoming really big and pretty much taking out the Earth and eventually collapsing down to a tiny little star called a white dwarf. But what happened if our sun was formed with another sun near it? The same process happens, but other stars are much beefier than the Earth, so they won't be destroyed. And what you will get is eventually material from the first star going on to this tiny little star called a white dwarf and making it get heavier and heavier. When they reach 1.38 times the mass of our sun, they explode with the power of 5 billion suns. They outshine an entire galaxy of stars. And they produce this amazing thermonuclear detonation, as we like to call it. From our perspective, they get brighter for about 20 days, and they fade away into oblivion. And we can use them as light bulbs whose brightness we understand to about 7%. That's better than a 100-watt light bulb you will go out and buy right now. So they are very, very useful things by astronomical standards. So I wasn't the only person who came up with this idea. There's actually 2 teams that were in a race to go through and exploit these supernovae to go and measure the past of the universe. And one was Saul Perlmutter, and one was me, and this is us about 12 or 13 years ago, and our teams were well known for disagreeing in public about how to do the experiment. But we really were ahead of large numbers of people dispersed around the world. And it was not an easy process. What we needed to do was to go find these exploding stars. Now, these exploding stars are really, really bright, but they're really, really rare. They only occur about once every 250 years in a galaxy like our own. So what we needed to do was go scan the sky and look at very, very distant objects and see what changed. So here is 1/8 of one image that we would take about every 2 minutes. There's 2 million by 4 million pixels in this image, so it's an 8-megapixel camera. You're like, yeah, okay. Well, this is 1995. So we were taking about 50 gigabytes of data a night. And in 1995, the machines I had a couple gigabyte hard drives, and they would take forever. The processors were much, much slower than my iPhone is now, and it was hard work to try to make this all work. And what we had to do is look for the needles in the haystack. Now, I'm going to show you where the object is here and see if you can pick it. It's right there. And how do we know it? Well, we took not one image, we took two images. And so what we would do is we'd go out, and then we would come back a few weeks later, and so this object emerged out of nothingness. This object is 5 billion light years in distance. Its light has taken 5 billion years to reach us. We are looking back before a time before the Earth was formed. So it really is quite magical that you can do this. So to get an idea of how this really works, I'm going to take you to Chile, to one of our observing runs. Here is the CTIO 4 meter, the twin telescope of the Anglo-Australian telescope. This telescope was equipped a bit better for doing this experiment than the AAT. The AAT does good stuff. Nick Sunseth, who helped form the team with me in 1994, is up manning the telescope. As the stars go by, we sip our Chardonnay and watch things go by, occasionally making sure that the $100,000 worth of telescope time we're doing is not going astray. So we would be taking data that looks not dissimilar to what I just showed you. Meanwhile, we would put that data down and be searched through in these sweatshops looking for objects that went blink in the middle of the night. Now, we had to do this very quickly because these objects, I said, are very rare, but we need to get spectra, and we need to use the largest telescope on Earth, the Keck telescope, and that's located 10,000 miles away in Hawaii, and we need to turn this around in about 1 or 2 days. And so there's no room for error. The Keck telescopes on Mauna Kea, as I said, were the largest telescopes. Here's Adam Rees and Alex Filippenko going through and taking our targets and identifying how much space had stretched between us and them, a key component. And we used to share these telescopes. Here's Saul Perlmutter, and he is there on the telescope using it the night after us. We share the telescopes because these facilities were unique in the world. It was technology that really allowed us to do this. It was new CCD detectors, the same thing you guys use in your digital cameras, coupled with computers and effectively these new giant telescopes. All right, so here's the results of 3 years of pretty hard work. I didn't sleep a lot during these 3 years. And what I'm showing you here is an experiment looking back in time, and I'm showing you here essentially the coasting universe. And I want you to look at the trajectory of a universe which eventually halts and starts to collapse. That is this line right here. Now you can look, each object, each exploding star is represented by a bar that shows you the range of which answer. You know, they're not perfect. We have uncertainty. And so each object doesn't tell you the answer. You've got to observe a bunch of them. These are nearby objects, and you'll notice that their bars follow here, but they also follow up here. You can't really tell what's going on. But when you go out here in the distant universe, you can see that in the past, the universe was not expanding faster and slowing down. Every object is above the line that says the universe is going to eventually halt its expansion and go in reverse. I was sad because that was sort of the answer I was hoping for. But the universe, I'm afraid, does what it wants. I was interested because when I compared it to the yellow part of the diagram, the other solution we were looking for, where the universe would be slowing down, well, some of the objects are consistent with that, but on average, it turns out, they're not consistent with that. If you go through and run the numbers, 9,993 times out of 10,000, you get, it's not the right answer. So it seems that the universe is doing something funny. It's speeding up over time. Now, okay, maybe we have a problem, maybe we don't. You can be worried, but at the same time, unbeknownst to us, the other team was getting exactly the same answer. So we had two groups that simultaneously converged to the same crazy idea. The universe was speeding up. Now, people often ask whether or not we had this sort of unique moment, and the answer is we didn't. It sort of happened, I guess, slowly over time where we had this realization. So these Type 1a supernovae measurements, these exploding stars in 1998, sort of indicated if we wanted to make the universe expand at a faster and faster rate, we had to go back to Einstein's solution. Einstein invented stuff that pushes rather than pulls, the stuff he called the cosmological constant, and which we now call dark energy. But we needed a lot of this stuff. We needed 70% of the universe to be this dark energy to make it work. It turns out we couldn't have a universe that only had dark energy. We also needed stuff that has normal gravity, stuff we usually call dark matter, and that needed to be about 30% of the universe to make it all go. So that was our first go, and as I said, Adam went through, and I guess if anyone had the eureka moment, it would have been Adam, but it's not clear to me that we just assumed when we first made the measurement, it was wrong. So this resulted, we have some issues here. Resulted in this year us being awarded the Nobel Prize. And here's the team. There was 20 of us in Stockholm. I don't have the other team Nobel Prize photo, I'm afraid. But there were several Australians involved in the other team. And we collectively got together and had a big party in Stockholm. The whole party in Stockholm is quite interesting because they give you a driver. My driver's name was, honest to God, Stig. So this is Stig, driving a BMW. We got around quickly. And I got to give a lecture, not dissimilar to this one. I got to meet the King of Sweden. And I got to to escort a princess who was 6 months pregnant down in front of 1,350 guests. So it's quite an exciting time to be part of. But I think, from my perspective, it really was time for the team to celebrate. And it was a great triumph, not really for me, but for science, that we're able to piece these things together. So what is pushing on the universe? Now, I told you about Einstein's dark energy already. Well, that is an idea that we want to think about. Is Einstein once again right? Remember, Einstein called this his greatest mistake. But my experience with Einstein is his greatest mistakes tend up to be my greatest triumphs. And so the question we have right now, is Einstein correct? Now, one of the ways that we can go out and test whether or not the supernovae measurements that we made were correct, it was done here in Australia. It was a map, a census of the nearby cosmos, where we went through, and I say we royally, I was not involved in this work, but they went and measured the position and redshift of 220,000 galaxies across the sky. And that allowed them to weigh the universe and see how much normal gravity there was. And when they did that, they found out that compared to a universe which was flat, remember that's the universe that's precariously balanced, there wasn't enough. It had 27% of the amount of normal gravity to be flat. You could also go through and say, well, what's pulling on the universe? We call that dark matter. Now, that stuff that is pulling on the universe is something we don't understand in detail. We can tell how much gravity there is out there, but it is a problem because we've never identified what does it. We see the gravity, but we don't know in detail what it is. We think it's probably some undiscovered particle, and it has gravity just like atoms, but it's essentially invisible. It'll travel, for example, directly through the Earth. We have particles that are like this called neutrinos, but we've weighed them, and they're not heavy enough to account for this stuff. So there seems to be something we're missing. Now, we can go through and we can see the effects of this stuff in what we call the cosmic microwave background. The cosmic microwave background is the picture of the universe we can make 380,000 years after the Big Bang. When we make the universe smaller and smaller, we make it hotter and hotter. At this time, the universe was 4,000 degrees and was glowing like the sun. Here we're able to take a picture in microwaves, a snapshot. And what we see here are sound waves, sort of waves of sound sloshing around in the universe. And the size of these sound waves we can calculate using physics almost exactly. And this allows us to really go through and figure some interesting things out about the universe, most of which is whether or not the universe is geometrically flat or if it's finite or infinite. So we're going to go through and essentially take a bunch of models, about 10 years worth of models, and we're going to put it down into a nice graphical sense. If the bumps are small, then that means the universe is infinite. If the bumps are really big, that means the universe is finite. And if it's just right, the bumps will sort of be in the middle. If you go through and compare that to the observations, what we find is that the universe is almost exactly flat. It's almost exactly the way the theorists said it was. It has 100 plus or minus 1% of the amount of material to be geometrically flat. So let's put this together. We have the cosmic microwave background said we have 100% of the amount of stuff necessary to be flat. We have these experiments which went through and looked at all the galaxies, and they said, well, 27% of that has got normal gravity. So that leaves us with 73% of mystery matter that doesn't have normal gravity. That's almost exactly the same amount of the stuff that the supernovae said had to be there to push on the universe. In detail, if you want to make these work, it has to be almost identical stuff to the stuff that pushes on the universe that we saw. So that was a big check, and it's one of the main reasons why people believe in detail the experiment that we did in 1998. So when it would appear in detail, we have a very, very funny universe. We put this all together. We think we have a universe which is 13.7 billion years old. It's 72% of this mystery matter that pushes. It's 24% this unknown particle that we can't see, but we can tell how much gravity there is. And only 4% of the universe is atoms, the stuff we're made out of and the stuff we can see. It seems crazy, but it predicts every observation we've yet been able to make. And so people like me are trying to break this model. I'm not trying to show that it's right. I'm trying to show that it's wrong. But at this point, we have been unable to do so, despite it being quite crazy. So dark matter is stuff like atoms. As the universe expands, the amount of dark matter in atoms stays the same. So its density gets less and less over time. Imagine I have an atom in a box. Now, if the universe is expanding, the box gets bigger, the atom stays the same, the amount of stuff in the box drops per cubic meter. Dark energy, on the other hand, is tied to space itself. If you want something that pushes on the universe, it has to be tied to space itself. And so as the universe expands, dark energy gets created with space, and so it doesn't change over time. So the amount of dark matter to dark energy changes over time. A long time ago, when the universe was more compact, there was a lot of dark matter compared to dark energy. As the universe expands, then the dark matter, the amount of it drops, dark energy stays the same, and at some point, it turns out about 6 billion years ago, the two changed places in their dominance in the universe, and we ended up in a situation where dark energy, in its battle against dark matter, won. Dark energy essentially overwhelmed the universe. So if we look and think of it, a universe which would have been slowing down because of all the stuff in it, all the gravity initially, and it's only recently, as the universe got bigger and bigger, that this stuff tied to space would overwhelm the universe and cause it to expand more quickly over time. So that's a prediction we can go out and test. The Hubble Space Telescope provides that. So I'm going to show you one of the most distant objects ever detected. And here we are sitting out in a field in Kansas, I think, and we're going to zoom in to a galaxy that contained an exploding star that it turns out was about 11 billion years before the Earth was formed. If we look in detail into this little galaxy right here, and a star exploded. Now I'm going to skip the cheesy NASA animation and just show you some other ones. And the Hubble Space Telescope, through Adam Rees, went through and did a series of experiments on these very distant objects. And what they found, looking at my diagram, is that in the nearby, this is about 8 billion years ago, in this part of the diagram, the universe was accelerating, was speeding up. But when we went way back in time, the universe was actually slowing down. And so that is exactly what is expected by a universe that has dark matter and dark energy. So that was one of the other confirmations that came about. So where does this lead us? Well, I want to talk about the future of the universe. Then the universe's future seems to be dominated by dark energy. It's expanding now. The more it expands, the more dark energy there is compared to normal stuff that has normal gravity. And this causes the universe to speed up. The more it expands, the more dark energy dominates it. The more the dark energy pushes, the faster it expands. It's a runaway. So this, trying to understand this dark energy, it seems like a pretty important thing to understand the future of the universe. It's actually considered one of physics' biggest questions because 72 or 73% of the universe is stuff we don't understand. So the easiest solution is what we call the big chill. Imagine that Einstein's dark energy is tied exactly to space itself. So when you double the amount of space, you double the amount of dark energy. Well, in this case, dark energy has won the battle of the universe, and the universe will continue to accelerate the cosmos at an ever-increasing rate. The creation of space itself eventually happens faster than light can make it through space. So in this case, galaxies that we can see now will eventually become invisible because the light that they're emitting will not be able to get to us. Space will be created so quickly. That means that eventually we're going to live in a galaxy, in a universe where we look out and we'll be able to do no cosmology. There will be nothing to see. Turns out the part of the universe that we're in has already collapsed due to gravity. Dark energy is not being created, and so we're safe in this universe. However, since we don't really understand dark energy, it turns out if you're a theorist, you can make it do anything you want. And so anything is possible until we understand dark energy. Dark energy might change in the future, slow the universe up, or even accelerate the universe at a faster rate than Einstein's version. So that leads to a really interesting possibility, which is that dark energy gets created more quickly than space. In this case, dark energy has won the battle of the universe will speed up. But every piece of the universe can now be affected by this stuff. The part of the universe we've collapsed down into is no longer safe. This stuff can eat in. And it will eventually, turns out, be able to rip every part of the universe away from every other part of the universe, even at the subatomic level. And that would leave what I would describe truly as nothing. So we like to call that the Big Rip. We have no reason to believe it's going to happen, but it is a possibility. Don't worry, it's not going to happen anytime soon. I think the earliest it could possibly happen is about 30 or 40 billion years from now. I think, though, in most cases, we really can expect that the universe will, at an ever-increasing rate, expand and simply slowly fade away, leaving a fairly boring future for us that I think of as being about as bleak of ending as one could have. I would much rather end in a bang than in a whimper. Thank you very much.